Let's do the polysaccharides now. We'll start off with amylose. Amylose is just an unbranched thousands of glucoses, and they're all hooked up alpha 1,4, alpha 1,4, alpha 1,4, alpha 1. Obviously, we're not going to draw thousands of glucoses. So normally what I do with amylose is I'll just draw 3 of them and just say, et cetera, it goes this way, and et cetera, it goes this way. So if you know how to draw maltose, just add in 1 extra glucose and then just put some dotted lines to show that it keeps on going. So let me show you what I'm going to be doing. I've got, here's a glucose, and then I'm going to do alpha 1,4 to another glucose, and then an alpha 1,4 to another glucose. So obviously it's not glucose yet. I have to fill in everything. OH goes down, OH up, carbon 6. OH goes down, OH up, carbon 6. Remember, this is carbon 2, OH, carbon 3, OH, carbon 6. And then what I do is I'll say, okay, there's an O here and it just keeps on going, and an O here and it keeps on going. And that way you're saying that, okay, this is just a small section of a very long molecule. This is amylose. Remember, it's a part of starch. Starch is made up of amylose and amylopectin. Plants make starch, and they store it in their starch storage cells. And starch is amylose and amylopectin. So amylose is basically thousands of glucoses. And they're all hooked up together, alpha 1,4. Okay, and you're going to see that when we hydrolyze amylose, when we break it down, you end up with just thousands and thousands of glucoses, or you could end up just cutting 2 sections. These 2, and you end up with a maltose. Okay, that's amylose, alpha 1,4. Have you guys heard of the enzyme amylase that's in your mouth, the salivary amylase, and you also have pancreatic amylase? That enzyme hydrolyzes or breaks down these bonds. And we'll talk a little bit about that when we're doing reactions. Okay, the next one is cellulose. Cellulose is also thousands of glucoses, but they're hooked up beta 1,4 glycosidic bonds. So we could do beta 1,4 the way I did the lactose and the cellobiose, sort of like in a diagonal. So I'm just going to do 3 of them like I did with amylose. All right, there we go. Hold on a second. Here we go. All right, let's fill it in properly. OH at carbon 2 going down, OH at carbon 3 going up. Here's carbon 6. OH going down at carbon 2, up at carbon 3, carbon 6, OH, OH, carbon 6. And then you got this guy just O, et cetera, and O, et cetera, et cetera. This is beta and beta coming in. So it just keeps on going, okay? This is thousands of them. Sometimes what they'll do is they'll put parentheses around it and then just say N equals hundreds or thousands. One key difference between cellulose and amylose: cellulose is very rigid. It's very, very linear, very straight, very rigid. Amylose tends to form coils. It's not branched or anything, but it tends to form coils in solution. Cellulose, very rigid. Think fibers of celery, long, rigid fibers, okay? We don't have an enzyme that breaks these beta 1,4 glycosidic bonds in cellulose. All right. Amylopectin is the other component of starch. Now, cellulose is made by plants only. We don't do it. Humans don't. Animals don't. Cellulose is made by plants, and it is part of the cell wall of a plant. Okay, but amylose and amylopectin, those are part of the starch storage cells of a plant. Amylopectin is branched. Amylopectin is made up also of thousands of glucoses, but it is branched starch. What do I mean by branched? You have alpha-1,4 glycosidic bonds and alpha-1,6 glycosidic bonds. So you have both glycosidic bonds. So it looks a little tricky, but let me try to show you what I mean by this. Let's say I've got, I'm going to draw a few of them here just to show you. All right, so here's the typical alpha-1,4 that you saw with amylose. Okay, so this is just keeps on going this way, all right? And let's say this is carbon-6. Now, this carbon-6 I'm going to hook up to another chain. So let's say I have another one over here, and it keeps on going this way. Hopefully you'll see what I'm trying to do here. So what happens is that the OH here and the CH2OH, H comes off, OH comes off as water, just like we did before. But notice this now is an alpha-1,6 glycosidic bond. This is an alpha-1,4. So if you look at the full structure that your book has, you'll see all the branches. And what happens is that you've got this long chain that's alpha-1,4, and then every maybe 15 glucoses or so, don't need to worry about the exact amount, you get a branch, and then another long, and then another branch, and then another branch. What do you guys need to know? You need to know that amylopectin is made up of thousands of glucoses. It's a branched polysaccharide. It is part of starch. Only plants make it. And you have both alpha-1,4 and alpha-1,6 glycosidic bonds here. And that's what it looks like. Now, the other branched polysaccharide is glycogen. The main difference between glycogen and amylopectin is that glycogen is made by animals and humans. Amylopectin is made by plants. But really, they look very, very much alike. So there's no point in me redrawing all of this. It looks exactly like this. Glycogen is a little bit more branched, so maybe instead of every 15 glucoses, it's branched even more. Again, the actual number doesn't really matter because you're not going to draw a whole bunch. You're just going to draw this amount. 2 glucoses this way, and then 1 coming out this way, and then dotted lines saying that it keeps on going. So what I'm going to do now is just erase the word amylopectin and throw in the word glycogen. And voila, you've got the structure of glycogen. All right? So glycogen is a branched polysaccharide. It is made by animals and humans. It is called, animal starch or human starch. We store it in the liver and in the muscle, and it's made up of thousands of glucoses. It's branched, alpha-1,4 and alpha-1,6. Okay, and that does it for all the structures for this chapter. The next thing on the what you need to know list says know what lactose intolerance is. You may know someone who is lactose intolerant, or maybe you are lactose intolerant. What that is the inability to hydrolyze the beta-1,4 glycosidic bond. So people with lactose intolerance have a really hard time properly digesting milk products because lactose is found in milk and all its products. It's found in milk, cheese, yogurt, anything that's made that's got some cow milk in it, or other types of animal milk too. But here's the thing. When you have yogurt or cheese, the lactose has been reduced quite a bit because the bacteria used to make the yogurt and cheese pretty much hydrolyze that glycosidic bond. But milk, yeah, it's got quite a bit of lactose. What happens to people who don't have the enzyme lactase, the enzyme that those of us who are not lactose intolerant have the enzyme lactase. So many of those people don't have that, so or they have an insufficient amount of the enzyme lactase. If that's the case, then you have that lactose in your intestines. You're not able to digest it. Only monosaccharides go through the villi, so the lactose is just sitting there, and then the bacteria start to work on it. So a lot of people experience gas, diarrhea, all sorts of fun GI issues. And that's lactose intolerance. You can read up more about that. Um, Now, you could go and buy the lactate milk. Guess what the lactate milk is? It's just milk with the lactose already broken down for you. So basically, the lactose is no longer lactose. It becomes the two monosaccharides, galactose and glucose. All right. Our last video will just deal with reactions of carbohydrates for this chapter, and then we will be all set and ready to move on. Okay.